We use an apparatus that allows a copper plate to swing back and forth through a magnetic field, like a pendulum. The plane in which the copper plate swings is parallel to the plane of the plate and normal to the direction of the magnetic field. As the copper plate enters the field, the changing magnetic flux induces an EMF in the plate, which in turn causes the free electrons in the plate to move, producing circulating eddy currents. Note that the magnetic field is directed from the north pole to the south pole of the magnet that provides the field. When viewed from the north pole side of the magnet, the induced eddy current is counterclockwise as the plate enters the field. As the plate enters the magnetic field, the external magnetic flux through the plate increases. Hence, by Lenz's law, the induced current must provide effective magnetic poles on the plate that are repelled by the poles of the magnet. Thus, here a north pole is induced over the surface of the plate facing the north pole of the magnet. As the plate leaves the magnetic field, the external magnetic flux through the plate decreases. Hence, again as per Lenz's law, the induced current must provide a magnetic south pole on the surface of the plate facing the north pole of the magnet. This is quite opposite to the case when the plate enters the magnetic field. The induced eddy current always produces a retarding force FB when the plate enters or leaves the field. This retarding force slows down the swinging of the plate and eventually brings it to rest. Thus, the oscillations of the plate are damped. When rectangular slots are cut in the plate, eddy currents and the corresponding retarding force are greatly reduced. This reduction in the retarding force is because the rectangular cuts in the plate prevent the formation of large current loops. Hence, the pendulum plate with holes or slots reduces electromagnetic damping and the plate swings more freely. Let us now explore the uses of eddy currents. Eddy currents are produced when a metal plate is subjected to a changing magnetic field, heats it. Hence, these currents are unwanted in certain situations. Reduction in the surface area of the plate helps in reducing eddy currents in the metallic cores of transformers, electric motors, and other such devices, in which a coil is wound over a metallic core. Eddy currents are minimized by using laminations of metal to make a metal core instead of using a single metal piece. The laminations are separated by an insulating material like lacquer. The plane of the laminations is arranged parallel to the magnetic field, such that it cuts across the eddy current paths. This arrangement reduces the strength of the eddy currents. Since the dissipation of electric energy into heat depends on the square of the strength of the electric current, heat loss is substantially reduced. Let us now study the applications of eddy currents. Strong electromagnets are situated above the rails in some electrically powered trains. When the electromagnets are activated, the eddy currents induced in the rails oppose the motion of the train. As there are no mechanical linkages, the braking effect of the train is smooth. Certain galvanometers have a fixed core made of a non-magnetic metallic material. When the coil oscillates, the eddy currents generated in the core oppose the motion and bring the coil to rest quickly. Induction furnace can be used to produce high temperatures and can be utilized to prepare alloys by melting the constituent metals. A high-frequency alternating current is passed through a coil which surrounds the metals to be melted. The eddy currents generated in the metals produce high temperatures sufficient to melt it. The shiny metal disc in the analog type electric power meter rotates due to eddy currents. Electric currents are induced in the disc by magnetic fields produced by the sinusoidal varying currents in the coil. Consider a circuit consisting of a coil having n number of turns connected to a source of EMF in which current can be varied with time. When the source current is in the direction shown, a magnetic field directed as shown is set up inside the coil. When the source current changes with time, the magnetic flux through the coil also changes and induces an EMF in the coil. This phenomenon is called self-induction. The flux linkage through a coil of n turns is proportional to the current through the coil and is expressed as n phi b is directly proportional to I. Replacing the proportionality symbol with a constant, we get n phi b is equal to L times the current I, where the proportionality constant L is called the self-inductance of the coil. Let this be equation 1. L is also called the coefficient of self-induction of the coil. When the current in the circuit is varied, the flux linked with the coil changes and an EMF is induced in the coil. This means d by dt of n phi b equals to L di by dt. Let this be equation 2. From Faraday's law, for a coil of n turns, the self-induced EMF E is equal to minus d by dt of n phi b. Let this be equation 3. Comparing equations 2 and 3, we get the equation E is equal to minus L di by dt. Let this be equation 4. It is important to know that from Lenz's law, the polarity of this induced EMF is such that it opposes the change in the magnetic field from the source current. Even Faraday's equation confirms that the self-induced EMF opposes any change of current in the coil. Thus, this self-induced EMF is also called back EMF. The self-induced EMF plays the role of inertia. It is the electromagnetic analog to mass in mechanics. Hence, work needs to be performed to establish a current in a circuit, and it is stored as magnetic potential energy. For a current I, at an instant in a circuit, the rate of work done is dW by dt is equal to modulus of E times I. Let this be equation 5. On substituting the magnitude of E from equation 4 in equation 5 and simplifying, we get dW by dt is equal to Li di by dt. Let this be equation 6. The total amount of work done can be established by integrating equation 6 on both sides. Thus, we get integral dW is equal to integral over 0 to I, Li di. Thus, the work done or energy consumed in establishing a current in the circuit is W is equal to half Li square. This expression is similar to the expression for kinetic energy of a particle of mass m moving with velocity v, which is given by E is equal to half mv square. This clearly shows that self-inductance L in electromagnetic induction is analogous to mass m in mechanics. Thus, self-inductance is the measure of electrical inertia. It opposes the growth and decay of the current in a circuit. Let us now calculate the self-inductance of a long solenoid. Let the length of the solenoid be L. the current through it Bi, the number of turns Bn, and its area of cross-section Ba. Let the number of turns per unit length of the solenoid be N, which is equal to N by L. The magnetic field induced in the solenoid due to the current I is B is equal to mu naught Ni. Let this be equation 7. Here, we neglect the edge effects of the solenoid, thus assuming the magnetic field in the solenoid to be uniform throughout. The magnetic flux is equal to the product of the magnetic field strength and the area. Thus, phi B is equal to Ba. Let this be equation 8. Using equation 7 and equation 8, we get the total flux linked with the solenoids is N phi B is equal to NL into mu naught Ni into A. Simplifying the expression, we get N phi B is equal to mu naught N square ALI. Let this be equation 9. We have already established that N phi B is equal to L times the current I. Comparing this expression with equation 9 and simplifying, we get the value of L as L is equal to mu naught N square AL. Let this be equation 10. If the space in the coils of the solenoid is filled with the material of magnetic permeability mu R, then L is equal to mu R mu naught N square AL. Let this be equation 11. Note that the self-inductance of the solenoid depends on the geometry and the permeability of the medium. An AC generator converts mechanical energy into electrical energy. In its simplest form, an AC generator consists of a rectangular coil mounted on a rotor shaft. The coil is also referred to as the armature. The coil is placed in a uniform magnetic field. The axis of the coil is normal to the direction of the magnetic field. The coil, or the armature, is mechanically rotated in the uniform magnetic field by some external means. Let the number of turns in the coil be N. The ends of the coil are connected to an external circuit by means of slip rings and brushes. The coil rotates, inducing an EMF and a current in itself. The current induced in the coil is fed into external circuits through the slip rings that act as terminals to the generator. Let us now find the expression for the EMF generated by an AC generator. Consider the area vector A. For the coil, the area vector is normal to the plane of the coil. Initially, let the area vector lie in the direction of the magnetic field. This implies that plane of the coil is normal to the direction of the magnetic field. Let theta be the angle between the area vector A and the magnetic field B at a given instant of time t. When the coil is rotated at a constant angular velocity omega, the value of theta at the instant of time t is given by the equation theta is equal to omega multiplied by time t. Let this be equation 1. The effective area of the coil which is linked with the magnetic field is A cos theta. From equation 1, it is clear that the effective area of the coil is a time-dependent function. In other words, the rotation of the coil causes the magnetic flux through it to change, thereby inducing an EMF in the coil. The flux induced in the coil at any instant of time is given by the equation phi B is equal to BA cos theta. Let this be equation 2. On substituting equation 1 in equation 2 and simplifying, we get the equation phi b is equal to BA cos omega t. Let this be equation 3. From Faraday's law, the induced EMF for a coil of n turns rotating in a magnetic field is given by E is equal to minus nd phi b by dt. The negative sign is in accordance with Lenz's law. On substituting the value of phi b from equation 3 and simplifying, we get E is equal to minus nd by dt of BA cos omega t. The strength of the magnetic field B and the area of the coil A are constants. The equation now transforms to E is equal to minus nBAd by dt of cos omega t. From differential calculus, we have d by dt of cos omega t is equal to minus omega sin omega t. Hence, the instantaneous value of the EMF E is equal to nBA omega sin omega t. Let this be equation 4. Note that nBA omega is the maximum value of the EMF that occurs when the value of sin omega t is plus or minus 1. That is, when theta is 90 degrees, or 270 degrees. This is because the change of flux is the maximum at these two angles of the coil. As the value of sine function varies from plus 1 to minus 1, the sign or polarity of the EMF changes with time. Accordingly, the direction of the induced current changes periodically. For this reason, this current is called an alternating current. Let us denote the maximum EMF nBA omega as E naught. Then, the instantaneous EMF E is equal to E naught sin omega t. Let this be equation 5. We know that omega is equal to 2 pi nu, where nu is the frequency of revolution of the generator's coil. Substituting the value of omega in equation 5, we get E is equal to E naught sin 2 pi nu t. Let this be equation 6. Thus, equation 6 gives the expression for the instantaneous value of the EMF. Earlier we have learned how an electric current is induced by the relative motion between a closed coil and a magnet. Electric currents can also be induced in a closed coil by causing a change in the magnetic flux produced by its relative motion with another current-carrying coil in its vicinity, or by a flux change produced by the same coil. Let us first understand the experimental setup that helps us demonstrate this phenomenon. The coil on the left is called the primary coil and is connected to a battery. Let the current in this coil be I1. The coil on the right is called the secondary coil and it is connected to a galvanometer. The primary and the secondary coils are placed coaxial and an iron core runs along the axes of the coils. Let B be the magnetic field strength due to the current in the primary coil. When the secondary coil is moved towards the primary coil, the magnetic flux through the secondary coil increases. As a consequence of the increasing flux, in the secondary coil. The current induced in it increases as it moves towards the primary coil. Let the current induced in this coil be I. When the secondary coil moves away from the primary coil, the magnetic flux through the secondary coil reduces. As a consequence of the decreasing magnetic flux, the current in the secondary coil decreases. The magnetic flux in the secondary coil, phi b, is directly proportional to the current I in it. The variations of the current in the secondary coil are directly proportional to the variations in the magnetic flux. Thus, the rate of change of flux is directly proportional to the rate of change of current. Let the number of turns in the secondary coil be n. Hence, the net flux change in the secondary coil, n phi b, is directly proportional to I. The term n phi b is called flux linkage. The constant of proportionality m between the flux linkage and the current is called the mutual inductance of the coil. Inductance is a scalar quantity and has the dimensions ml square T power minus 2 A power minus 2. The SI unit of inductance is Henry, named after the scientist Joseph Henry, and is denoted by H. 1 Henry is equal to 1 Tesla meter square per ampere. So far, we have explored the experimental setup with two coils of the same radius placed besides one another. Let us now consider an example in which two coaxial solenoids induce current into one another. Consider two coaxial solenoids S1 and S2 of length L. Let the radius of the inner solenoid S1 be R1 and the number of turns per unit length be N1. Let the radius of the outer solenoid S2 be R2 and the number of turns per unit length by N2. Let N1 and N2 be the total number of turns in coils S1 and S2. Thus, we have N1 is equal to N1L and N2 is equal to N2L. When a current I2 is passed through the coil S2, a magnetic flux is set up within the coil and this flux is linked with the coil S1. Let us denote this magnetic flux by phi1. Let this be the flux per turn of the coil. Then, the total flux linkage with solenoid S1 is N1 phi1 equal to M12 I2. Let this be equation 1. M12 is called the mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred to as the coefficient of mutual induction. The magnetic flux is equal to the product of the magnetic field strength into the area. The magnetic field strength B2 due to the current I2 in solenoid S2 is given by B2 equal to mu naught N2 I2. Let this be equation 2. Area of the coil in solenoid S2, A is equal to pi R1 square. Let this be equation 3. Multiplying equations 2 and 3, we get the value of the magnetic flux in the coil of solenoid S1 as phi1 equal to mu naught N2 I2 into pi R1 square. Let this be equation 4. Also, we know that N1 is equal to N1L. Let this be equation 5. On multiplying equations 4 and 5 and simplifying the right-hand side, we get the expression N1 phi 1 equal to mu naught N1 N2 pi R1 square Li2. Let this be equation 6. Equating the right-hand side expressions of equation 6 and equation 1 and simplifying, we get M12 is equal to mu naught N1 N2 pi R1 square L. Let this be equation 7. Note that for these calculations, we neglected the edge effects and consider the magnetic field to be uniform throughout the length and width of the solenoid S2. Also, solenoids of equal length were chosen. This is a good approximation, keeping in mind that the solenoid is long, implying L is much greater than R2. Let us now consider the case in which current I1 is passed through the solenoid S1. This current produces magnetic flux, which is also linked with the solenoid S2. Let the magnetic flux per turn linked with solenoid S2 be phi 2. Then, the total flux linkage with solenoid S2 is N2 phi 2 is equal to M21 I1. Let this be equation 8. M21 is called the mutual inductance of solenoid S2 with respect to solenoid S1. It is also referred to as the coefficient of mutual induction. The magnetic flux is equal to the product of the magnetic field strength into the area. The magnetic field B1 due to the current I1 in solenoid S1 is given by B1 is equal to mu naught N1 I1. Let this be equation 9. Area of the coil in solenoid S1 A is equal to pi R1 square. Let this be equation 10. Here, we assume the flux due to current I1 through S1 is completely confined to the solenoid S1 only. This is because the solenoids are very long. On multiplying equations 9 and 10, we obtain the magnetic flux per turn through the coil of solenoid S2 as phi 2 equal to mu naught N1 I1 into pi R1 square. Let this be equation 11. We also know that N2 is equal to N2L. Let this be equation 12. On multiplying equations 11 and 12 and simplifying the right-hand side, we get the equation N2 phi 2 is equal to mu naught N1 N2 pi R1 square L I1. Let this be equation 13. Equating the right-hand side of equation 13 and equation 8 and simplifying, we get the expression M21 is equal to mu naught N1 N2 pi R1 square L. Let this be equation 40. Comparing equations 7 and 14, we get M12 is equal to M21. Let M12 is equal to M21 be equal to M, which is equal to mu naught N1 N2 pi R1 square L. Note that the mutual inductance is neither dependent on the current nor the magnetic flux. It is dependent on the geometrical dimensions of the solenoid. This expression is true when the medium within the solenoids is air. If the medium within the solenoids has relative permeability mu r, then M is equal to mu naught mu r N1 N2 pi R1 square L. This equality M12 is equal to M21 holds good for long coaxial solenoids and is far more general. Even though the inner solenoid S1 is much smaller than the outer solenoid S2, calculation of flux linkage with inner solenoid is possible as it is effectively immersed in the uniform magnetic field due to the current through the outer solenoid. Thus, calculation of mutual inductance M12 is easy. However, in this case, it is difficult to find the flux linkage with outer solenoid due to the current through the inner solenoid. This is because the magnetic field due to the inner solenoid would vary across the length as well as the cross-section of the outer solenoid. Thus, calculation of mutual inductance M21 becomes difficult. Let us now take a look at how a change of current affects mutual inductance. Let us consider an experimental setup in which there is a coil C1 that is connected to a galvanometer G and another coil C2 connected to a battery. EMF is induced in coil C1 wherever there is any change in current through coil C2. Let Phi1 be the flux through coil C1 of N1 turns when current in coil C2 is I2. We know that N1 Phi1 equal to Mi2. The rate of change of current is equal to the rate of change of flux. This means that dN1 Phi1 by dt is equal to dMi2 by dt. The EMF induced in coil C1 is given by E1 is equal to minus d N1 Phi1 by dt. This implies that E1 is equal to minus M di2 by dt. Remember, only flux and current change. Hence, M is a constant. This equation shows that a varying current in a coil can induce EMF in a neighboring coil. Let us now solve an example to reinforce our understanding of mutual inductance. A current I passes through the outer ring of two coplanar concentric loops of radii R1 and R2. R1 is much greater than R2. What is the mutual inductance between the two loops? The magnetic field induced by a current I at the center of the ring of radius R1 is B1 equal to mu naught I by 2R1. The flux through the ring of radius R2 is given by Phi21 equal to B1A2. This implies that Phi21 is equal to mu naught I by 2R1 into pi R2 square. Mutual inductance M is given by Phi21 by I. On substituting the value of Phi21 and simplifying, we get the value of mutual inductance as mu naught pi R2 square by 2R1.